Okay, so we've talked about vectors and how to kind of interpret them and think about them a little bit. So now let's apply vectors to 2 and 3 dimensional motion as the kind of extension of one dimensional motion that we had in the last unit. So we'll just jump right in. We had defined our average velocity. So we had average velocity to be equal to the change in position over the change in time. This was just one dimensional. We want the 2 and 3 dimensional case of this. So now we need vectors. Our velocity is not just going to be moving in one direction. Our velocity we may be moving in 2 directions. So instead of the average velocity, what I want now is the average of the velocity vector. And instead of just a change in position right here, I want the change in my position vector. So I'm going to use r for this vector, and it's going to be the change in my position vector. All right? So it's delta r over delta t, because this r vector right here includes both the x and the y position. So that's our average velocity. Now we also had instantaneous velocity. In one dimension, instantaneous velocity looks like this. We have the instantaneous velocity was equal to the derivative of position with respect to time. But again, we are in multiple dimensions now. So we want the instantaneous velocity vector. And it's not just going to be the change in x or just the change in y. We're not moving in a straight line now. This is going to be the derivative of the position vector. And this is worth talking about a little bit more. The derivative of the position vector, we say we take it component-wise. So this position vector is going to be some distance in the x direction horizontally, and then it's going to be some distance in the y direction vertically. So we have our I hat and our j hat to represent the directions, and we're adding the two components. This is the component representation of this vector. If we're trying to take the derivative of this vector, dr dt, it's very simply just taking the derivative of each component. So it's the derivative of the x component with respect to t plus the derivative of the y component with respect to t in the vertical direction. So it's just component-wise. And again, when we do some examples of these, we'll see a more in-depth look at how to actually do this. But so our instantaneous velocity vector is going to be the derivative with respect to time of the position vector. And then the analogs with acceleration, I'll use yellow. So the average acceleration, we had average acceleration, and we defined that as the change in velocity over change in time. And similarly, now we're not moving in only one dimension. So we want the change, the average average acceleration vector. It's going to be the change in the velocity vector divided by the change in time. And then we can keep moving on to what about the instantaneous acceleration? Previously, we had defined that to be the derivative of velocity with respect to time, but now, in more dimensions, the instantaneous acceleration vector is the derivative of the velocity vector, which is going to be similar to the position vector in that we just take the derivative of each component. So it's the derivative of the horizontal component in the horizontal direction plus the derivative of the vertical component. This is Vy, velocity in the vertical direction with respect to t, and times our vertical unit vector j hat. And again, unit just meaning magnitude 1. All right, so these are our vector analogs of those familiar equations from one dimension. And we can extend this one a little bit. So this derivative of the velocity in the x direction, well, that's just going to give us the acceleration in the x direction times I hat. And similarly, the derivative of the velocity in the y direction here, well, that's just the acceleration in the y direction. And of course, times the unit vector j hat. So all of our vectors we can represent component-wise. We could expand the change. We could have a change in velocity vector. It would be the difference of your velocities in the x direction and the difference of your velocities in the y direction at two different points in time. We can always represent a vector in its component form if we have enough information, and it's always useful to do so.